Hi, everyone. Welcome to the conference and happy International Women's Day. My name is Stephanie Rivet.
And I'm Tirza Abbott.
And we are really happy to welcome you to the third annual Women in Microscopy Conference. We are really moved by the interest that we've had in this conference from diverse fields and people from all around the world. And it's been really exciting to see how much this conference has grown in the last 3 years.
So the aim of this conference is to highlight women in the broad field of microscopy and provide a space for discussing some key issues that are central to many people's experiences as scientists. We have a very inspiring group of speakers and panelists here today, and we're very excited for you to meet them and learn from them.
We're really aware that there's many forms of diversity and a lot more work that needs to be done to make this a more inclusive field for everyone. And we're hoping that in some small way, this conference can help raise awareness of some of these issues and galvanize some of the changes that we need to make this a more equitable field.
This conference, of course, would not have been possible without the support from our incredible planning committee, both from the NUANCE Center here at Northwestern University and the Microscopy Society of America's Student Council. So before we kick off this event with the keynote talk, we would like to introduce Professor Vinayak Dravid, the founder and director of the NUANCE Center, and Louisa Mezach, the Student Council President, to briefly introduce these two organizations.
So a couple quick reminders to keep yourself muted during the presentations. We will have time for questions at the end, and you can ask your questions either by raising your hand and someone will call on you, or you can put your questions in the chat or send them directly to the moderators, who will be first Louisa and then Aubrey. So now we'll get started, and Professor Dravid, if you want to say a few words about the NUANCE Center.
Just a few words, just to, again, this is a fantastic event. I'm so proud of all of you for organizing this, including the student committee from MSA. So I won't belabor the point. I just want to take a moment to welcome everybody to this what has become a capstone event in the portfolio of NUANCE Center outreach. And when it started a couple of years ago, little did we know that this will become mushroom into such an amazing event. And I'm very proud and excited to be part of it. And my compliments and congratulations to both of you, but also MSA Student Council and others who participated and to make this happen. It's a very smart event, as you'll see, multiple format, multiple representation. So I'm very excited to be part of it. And please check us out at the NUANCE Center of the Shine Resort, which is the NSF Center. And I think the event is about you guys. So why don't I pass the event back to you, Tirza and Stephanie, and go for it. Congratulations.
Thank you. Oh, yeah. So Louisa, if you want to say a few words about the Student Council.
Thanks, Steph. So as Stephanie and Tirza mentioned, I'm the president of the MSA Student Council. And on behalf of the Student Council, it really is a true privilege to help host this conference. So our mission is to foster growth and encourage engagement of our student members within the microscopy community. And in light of this, we're really excited about a new initiative to help fund student travel to their local microscopy meetings or workshops or short courses. We're also beginning to take applications for elected positions within Student Council. It's a really great way to expand your professional skills and meet others in the field. We're also very excited for this year's PMC, which takes place July 22nd, the Saturday before M&M. We're planning a full day of technical and career workshops for students, postdocs, and early career professionals. We have a little bit of something for everyone. So I'll include information about everything I mentioned so far in the chat, but before I introduce our keynote speaker, I really wanted to share just a few thoughts about the importance of an event like this. So we all know the story of Watson and Crick, who in 1962 were awarded the Nobel Prize for their discovery of DNA structure. And it was finally recognized many years later that Rosalind Franklin's work in X-ray crystallography was essential in understanding the molecular structure of DNA. Now, while there's an argument for her untimely death being the reason she wasn't included in the Nobel Prize, there are endless stories like this. And what's surprising to me is that these stories continue to the present times. As recently as 2014, for the light microscopists in the audience, the Nobel Prize was awarded to 3 gentlemen for developing single molecule localization microscopy. However, Dr. Yichao Zhang, a female microscopist who developed this novel technique in parallel, went completely unrecognized. So while events like this are crucial for highlighting the works of historically excluded minorities in the field, I wholeheartedly hope that, at least in my time, we won't need separate events like this to focus on the accomplishments of the undervalued in our field, because they'll just be equally represented and recognized. They'll just be scientists. They won't be female scientists. So until then, and without further ado, it's my pleasure to introduce a leader in the fields of advanced microstructural characterization, irradiation embrittlement, and the technology of materials for nuclear power applications, Dr. Grace Burke.
Thanks very much. I appreciate your kind introduction. And I'm going to start off by sharing my slides and give you a bit of background on myself and my career path, and then move into the exciting research that still makes me very, very proud and happy to be active in the field. So let me make sure I'm doing this properly. Working with the screens. Can you see one or two slides?
It looks really good.
Fantastic. That's absolutely great. Okay. Again, thank you. I'm presently a corporate fellow at Oak Ridge National Laboratories in the Materials Science and Technology Division. I'm also a professor emeritus at the University of Manchester, as I retired there at the end of September in 2021. And I'm so thrilled to celebrate today with International Women's Day and this fantastic conference series. So basically, I wanted to give you a bit of background on myself and then go into the sort of meat of this presentation, which is exploring materials degradation in extreme environments. And by that, I mean nuclear power systems. And you'll see the need for microstructural analysis as we strive to understand materials degradation phenomena and how we can improve materials. So I'll talk a bit about the approach, techniques, and focus on the applications. And there'll be two. One involves stress corrosion cracking, and the other is irradiation damage, particularly of steels, and then a bit of an outlook summary and some acknowledgements. And I should point out that I am a metallurgist, a physical metallurgist, as they say over here. I'm speaking to you from the UK, from very cold and dark Manchester, where it's even colder than Chicago. Okay. So a bit about me. Well, although I was born in Baltimore, Westinghouse brat, since my father was an engineer from Westinghouse, but was working in Baltimore, but raised in Pittsburgh. Now, my background is a bit, well, maybe slightly unconventional, but I went to an all-girls high school and got interested rather sheepishly in science projects from a wonderful biology teacher that I had in terms of describing cells and the like, but with a statement that really fascinated me, that there were parts of cells that were so small that it wasn't possible to image them. This was in the late 60s. And at that time, there was some amazing microscopy, TEM work going on, but it hadn't made it into the textbooks. Anyway, I ended up getting interested in doing crystal growth in gels and had a great opportunity from an NSF-sponsored local material science program. So that introduced me to materials and metallurgy. I ended up attending the University of Pittsburgh, majoring in metallurgical engineering, had a great time there, had a wonderful opportunity to spend a summer at University College London in the crystallography group between my sophomore and junior year, then back to school and got interested in student government, which was a bit off track, I guess. While I was at Pitt, I met Michael Burke, who was a metallurgy graduate student from Cambridge University. And while I was there, I was going to stay and do a master's degree, but I happened to be in the right place at the right time and had an offer to do a PhD with Peter Swan. And when he left Imperial to start Catan, I continued my work with John Humphreys at IC. But I did manage to get a bit of additional R&D experience by spending a summer at US Steel's research labs before crossing the pond. Well, carried on with my thesis, intergranular stress corrosion cracking of sensitized austenitic stainless steel, and got to use the amazing 3-story high voltage electron microscope that was located at Imperial in central London, along with the new instruments that were coming along, such as analytical electron microscopes. Well, things got rather busy. I had my PhD viva in London 2 weeks before my wedding in Pittsburgh to Michael. And that was very interesting at the time because that was a Mr. and Dr. event. So then back to the UK and Sheffield, back to Pittsburgh, and we decided to go into industry type R&D, US Steel research for me, and Westinghouse for my husband. So I eventually joined Westinghouse Science and Technology Center, and after about 7 years transferred to the Bettis Atomic Power Laboratory. And I had been doing a lot of work with my Bettis colleagues. And that transition occurred just after our daughter, Eileen, was born. So things carried on, interesting careers, lots going on, but then we decided to make a career change. And in late 2011, we crossed the pond again, this time for the University of Manchester and the School of Materials. And as I'd mentioned earlier, in late 21, I came back to the United States and joined Oak Ridge National Laboratory. So in a nutshell, most of my career has been in industry R&D, and I should point out in male-dominated industry, and about 10 years in academia. So the thing I want you all to be aware of is you never know where your path is going to lead. You need to be open to new opportunities, even ones that you think, how will this ever impact me? I started out very focused on classes, got involved with student government in the school, made some fabulous connections, which actually, in the end, put me in the right place at the right time to take the PhD position at Imperial. That unique opportunity to study abroad kind of got my taste up for traveling, going back to the UK, and also crystallography. At University College London, I didn't fully appreciate it at the time, but was a very historical place and very prominent, the crystallography side, because Kathleen Lonsdale, who also was a major trailblazer in crystallography, was a student of Bragg's. And then when I was over there, I was under the direction of Dr. Judith Millage, who was Kathleen Lonsdale's student. And there was a very nice graduate student there who was just starting out, who is now the head of that area of research, Professor Ian Wood. But anyway, these things, all these connections are just amazing. So back to Pitt, back to student government, and Michael Burke, the metallurgy graduate student from Cambridge, and I eventually started dating, eventually getting married. And we just thought this was, wanted to carry on doing our PhDs. So we both went back. And again, going back to the US and going into research. But what was really important was that I get a job on my own and not one of these, at the time, it was very unusual to have a husband and wife, both with PhDs. And frequently it was, oh, we're looking at the man, but we'll find something for the woman. So it was very important to me that I get a job on my own. Now, I'm not sure if I've stopped sharing, so, or if it's my...
It looks like you have, Dr. Burke. We don't see your
Oops.
slides.
Sorry. Okay.
Okay, they're back.
Okay, super. Thank you so much. Great. Okay, and I wanted to point out the other thing is it is important to get involved in your career, in your societies. I joined MSA, EMSA at the time, which the joke at the time was that it was the English Microscopy Society of America, but it's a super organization, great members, and I've met many, many friends. And I joined that fairly early on, and then RMS in '87. Well, our daughter, Eileen, was born in '94, and she became quite a traveler because I actually would take her to conferences. And that was possible due to a great supportive husband who would take his vacation time and come along. So her first conference was at 2.5 months. And the first time she saw the ocean was in Rio when she was 18 months. So a bit of a timeline for me, but going through high school and science projects, and of course you'll notice those dates, which are like really ancient, but going to University College London, Imperial College, Westinghouse, Bettis, and again, even at US Steel's research lab, getting involved with a broad range of materials and techniques. I accidentally, atom probe field ion microscopy started me out on using independent collaborative techniques. And then Westinghouse broadening that materials even further and tending to focus on light water reactor structural materials. And then at the University of Manchester, where I was a professor and the director of the Materials Performance Center, and for about 4.5 years, also the director of the Electron Microscopy Center there. So, and you can't talk without showing some images. So here they are. At Imperial College, visit from Princess Margaret, and I was demonstrating the 1,000,000-volt microscope. Peter Swan and myself at Carnegie Mellon University many years later. Those of you that are analytical electron microscopists probably know of the Cliff-Lorimer relationship. This is half of it. This person is half of it, Graham Cliff, along with my student Giacomo, myself. Well, Peter Swan is here. His daughter Karen came to our M&M symposium in memory of Peter Swan on in situ microscopy. And then, of course, the family photos, Michael and Eileen in Rio on Leme Beach, 3 Pitt graduates, a bioengineer, and then my husband and myself. So anyway, that's me, and I wanted to now to hit some scientific things, but I'm going to be very happy to answer any questions along the way. Well, we're interested in moving to a low carbon energy future. So there's a lot of interest in energy sustainability and diversification of sources. But renewables are great, but they're not sufficient. And we still have to address issues with storage and the power grid for distribution. But nuclear energy, we've got a lot of existing designs with light water reactors, new designs, and it's well positioned to help us out of this bind. So we want to take advantage of advances in materials development, manufacturing, joining, and the like. And that's moving along quite nicely so that we've got small modular reactors and advanced modular reactors underway in terms of prototypes being built. And we're looking at that to really help solve our problems. But the bottom line is we still need research into the effects of the environment and radiation on materials. So we've got the issue of degradation of materials in these demanding environments, but they extend beyond nuclear, other forms of environmental degradation as well. And we tend to do that as metallurgy, material scientists, in terms of measuring properties as a function of environmental exposure, or in the case of nuclear, irradiation damage. And again, what we're after is identifying the physical changes in the material that have occurred that are associated with that degradation in performance. And to do that, we need detailed microstructural characterization. So we can identify those changes and then develop models to predict performance, and as well develop improved materials or processing, heat treatments, or even component designs for new and existing plants. Bottom line, the message is microstructure controls performance. Well, as this is a Women in Microscopy meeting, I can't go without saying something about the techniques we use, the instrumentation. A lot of research on with our SEM-based characterization for imaging, SEM-based energy dispersive X-ray spectroscopy, electron backscatter diffraction, and then moving on to cross-sectional specimen preparation, the site-specific nature when we have to study the structure in a certain location. And that's done these days with focused ion beam instruments. So that's also a very important component. And then there's the microscopy itself, the analytical characterization using transmission electron microscopy or STEM. And in that case, a variety of instruments can be used. And in my research, we tended to use going back to earlier instruments, which were still very robust and functional, the Philips CM20, the Talos F200 with Super X, so the 4 silicon drift detectors, which has really revolutionized our capabilities, and of course the Titan. I highlighted here something that you may or may not be very familiar with, but there still is a great need for conventional TEM specimen preparation. Things as simple as twin jet electropolishing techniques, because of the necessity to look at variability within a material. And we really need to do that by looking at large areas. And then now, in situ capabilities. When appropriate, we can do some amazing things with those. And the example that I'm going to talk about here is with protochip systems. The atmosphere gas cell will be the example for you, although we also do work with the protochips, the Poseidon Select. So stress corrosion cracking, for those of you that are not familiar, it's also known as environmentally assisted cracking, but basically it's the premature failure of a susceptible material in a reactive environment under a tensile stress. So we've got that standard Venn diagram over here. And we want to point out that, again, the material must be susceptible or
institutions.
Everyone, please make sure you remain muted. Thank you. Dr. Burke, you're muted.
Oh, thanks. Okay, no problems.
Not you.
So material, it can be a material that has been treated so that it becomes susceptible. So you need to be careful there. The environment can be reactive or described as a specific chemical environment that will not lead to material degradation on its own. And the stress could be external or residual. And, oopsie, okay, why am I not? Okay. And so I tell the students, you must have all 3 for SCC. Then there are lots of special tests that can be done to measure crack growth rates and the like, but we're not going to be talking about that at the moment. But the second part of the talk, when I get into the actual research, will deal with irradiation embrittlement, which is a loss of toughness due to neutron irradiation damage in the material. So I'm going to show a Sharpie impact transition temperature curve. So we have small specimens. What we have is a function of test temperature. Our material goes from being fairly brittle with low impact energy to a fairly ductile failure at a higher impact energy. So this is our non-irradiated. When we irradiate it, we can have a shift. So the important part of this is where we used to be ductile, have ductile behavior, we now can have brittle behavior. And that is what we want to avoid. And we want to understand how this happens. So the reason that we are interested is because the reactor pressure vessel, which is containment structure, for a pressurized water reactor, it's an irreplaceable component that isolates the reactor internals and the core from the external environment. So factors that we're interested in terms of studying this degradation is the composition of the steel or the weld of interest. We're interested in the neutron dose or fluence and the dose rate or flux, as well as the irradiation temperature. These will all have a big effect on the material. And to give you an idea what we're talking about here, since a lot of us tend to work with fairly small specimens, this is a ring forging that is in the beltline region of a pressurized water reactor. And here is our equivalent scale bar. Here is one of the engineers involved with construction. So they're quite large. So we've got stress corrosion cracking and irradiation damage. So we're looking at stress corrosion cracking, and now we'll go through and show you some research. We want to know the physical changes associated with initiation and propagation of cracks. And in terms of this, we also are interested in knowing the things that we've not been able to understand up to this point. Are there precursor events that will lead to SCC initiation? Then the questions that come to mind are, can we modify or optimize the material to mitigate susceptibility? And can we ultimately develop experimentally informed models to predict SCC? Well, a lot of work, stress corrosion cracking has been around for well over 100 years, different materials. And characterizing the material is really important. And so I know I probably sound like one of those real estate programs, but what is really critical is location, location, location. I've got some images here. These are just backscattered electron images, but this is an austenitic stainless steel and nice microstructure. And we could study this from our components. We could study this microstructure and try to figure out why is it susceptible to SCC. However, these are metallographic cross sections prepared that go to the outer surface. So this is the region that is in contact with the environment. And you can see these are much heavily deformed with an ultra fine grained microstructure at the surface. So lots of deformation. So we're looking at two different things. Location is important to keep in mind. And doing those as well, we want to know when we generate our data on bulk reactions and bulk materials, can we apply any in situ characterization to this study to trace relevant reactions in real time? Can we see the evolution of those changes? And is that fundamental understanding then something we can apply to develop improved models or alloys? And I just have two examples here. One is some dissolution of a manganese sulfide inclusion in distilled water. This is in a liquid cell. These are STEM-EDX elemental images just taken from the material in 1 atmosphere of air in the cell, and then after 2 hours in distilled water. So these are taken in the microscope in the cells. You can see there's water present because of the oxygen that we're able to pick up as well while these are dissolving. On the other hand, we've got cross-section of some alloy 600 specimens that have been exposed, and you're going to see more about those later and why that's important. So the objective we have is to understand these precursor events. And this is just initiation and propagation of cracks, which is pretty well known. Roger Staley and Renata Killian looked at this, breaking it down, but Renata added something very important. The need to consider what is the condition of the material before it sees the environment. So she termed a non-penetrative surface. So can we trace this and just see how this leads to propagation? Okay, so the alloy of interest is a very kind of simple, straightforward one. It's termed alloy 600, nickel with about 15 weight% chromium, about 9 weight% nickel, but you'll see low amounts of some other alloys here. And I would call your attention to the titanium and the aluminum here. Solution annealed, 1100 C, water quenched, polished, and another backscattered electron image where you can see a nice recrystallized microstructure, but also some very fine darkly imaging features at the grain boundaries that doing TEM and electron diffraction, they've been characterized as M23, identified as M23C6 carbides. Now we're going to test this, and this is done in a very simple system. My colleague Fabio Cennini and two of our students, Giacomo Bertolli and Liberato Volpe, had modified and improved. I had attempted this back in 1978 and I wasn't successful, so I'm very pleased with this. Anyway, hydrogenated steam, very simple. We bubble water through, we superheat it, the steam, and we've got hydrogen here, we mix it, and it just flows through this reaction tube, comes out, goes into the water. Very simple atmospheric pressure. But to look at the effect of stress, strain specimen, we've got a 4-point bend coupon in here too. Again, the result of some lovely work by Liberato Volpe. So let's have a look at the microstructure of these materials. So when we do an unstressed coupon, have a look, do the cross-sectional TEM characterization, we see that we've got some oxide on the grain boundary, and the boundary's moved a bit. Is it migrated? What is it due to? Well, careful TEM characterization, electron diffraction and dark field have shown that it's possible to image the ultrafine M23C6 carbides that had formed on the grain boundary during the quench, that water quench, and nicely delineating the position of that original grain boundary. So we know that the boundaries are starting to migrate. Can we get a better idea globally without doing a huge number of fib cross sections? And of course, you can by very careful secondary and backscattered electron imaging on the as oxidized surfaces or the as reacted surfaces. And you can see those squiggles on the grain boundary. I think, let's see, yes, I think I need to be on this screen, and where it has migrated. When we look at those fib cross sections using the talos, we can see very clearly that we have some pronounced chromium depletion. We also have chromium oxide formation, and the nickel map shows this very clearly as well. The boundary has undulated and we've got nickel-rich regions, but also some titanium and some aluminium is present. So we've got what actually is diffusion-induced grain boundary migration, and that's associated with this SCC precursor phenomenon. We're having very rapid diffusion of chromium out of the material to form the surface oxide and then start to oxidize along the migrated grain boundaries. So we can see this at various temperature, but hey, is it relevant to a light water reactor? Well, we looked at the hydrogenated steam, we looked at steam, and we looked at water exposures, and we're assessing the extent and the consistency of Diggum as a function of temperature. And well, it's only 3 points. However, you can draw a line through them. And that means we can get a slope, which tells us that the mechanism is consistent across that temperature range. So it really actually is relevant. Well, so we've got that preferential intergranular oxidation, but does it lead to stress corrosion cracking in the susceptible environments, which happen to be reducing environments? Will it lead to stress corrosion cracking? So some very lovely work by Liberato Volpe in terms of looking at 4-point bend tests in either oxidizing or reducing conditions in the environment of interest. So here's with unstressed, and here is what happens when it's stressed. We do see that we have a lot of cracked, undulating grain boundaries here. Possible crack initiation along the migrated grain boundaries? Well, we must do a lot of work, many grain boundaries to assess that. And those data are presented here, but what I want to point out to you is while there's very small amounts of preferential intergranular oxidation under oxidizing conditions, under reducing conditions, we get some significant cracking down the boundaries, particularly when we're close to this magic nickel-nickel oxide transition. So let's look at that under stress. We can do that. We see our migrated grain boundary, we have our crack, and because we're doing TEM characterization of this, we can do selected area electron diffraction and index the various oxides that are present, and we can image the various ones. So we've got the spinel, the Fe3O4, and we can also index the chromium oxide. And looking at this in more detail in the talos, we've got very clear diffusion-induced grain boundary migration. Some superposed maps here give a hint with chromium oxide and where the aluminum oxide is located, and titanium oxide. So we can see that those are actually along the center, on the crack itself. So we can get a mechanistic understanding. We've got what's going on and look at how these oxides and the preferential intergranular oxidation is playing a really important role at SCC. What I want to do is just show you what we can do with in situ work to study this. And this is again using the protochips atmosphere system in our Titan. The one thing that I want to highlight for you is that the specimens that we are exposing are thick specimens. I know it doesn't sound like it's very logical, but we need to make sure that we're not governed by surface effects. So we need to be thick. And we're going to do very simply bubbling gas, hydrogen gas through water. And we're going to we looked at several temperatures, and I'll just show you some examples. Oh, this is the hybrid specimen prep technique from electropolished foils. to fib out a region of interest and then tack it down the cell. This is not for the heating stage, but this was for a liquid cell experiment. And the schematic of what we're doing in terms of putting our gas, bubbling our gas through water and then into the cell. Set the pre-tank, pre-filled tank, and then into the gas cell. So this is what the sample looks like prior to going into the cell. And it's just tacked down with platinum on the side. So this was about 200 to 300 nanometers in thickness. And here I'm just going to show you what the exposures were like at 400 Celsius under 1 atmosphere, 1 bar gas. After 6 hours, our HDF image, we can see that we have chromium depletion, nickel enrichment, a little iron depletion as well. And then after 26 hours at temperature, the chromium depletion has expanded, nickel enrichment has expanded, and we can see a linear trace of titanium and aluminum. Now, I want to point out as well that these are raw data. These are not processed. This is as collected. The reason being that we're looking through our silicon nitride windows. We're also a 5 micron gap. We have gas in there, and we're just showing you the raw data. So with the sample, what we can do is cut it. Afterwards, it was thick. This was about 250 nanometers in thickness, pardon. And we can see that our boundary was a little displaced, but we've got our chromium oxide film on the surface, chromium depletion, nickel enrichment, iron depletion, and amazingly, evidence that the titanium and aluminum were important in this as well, that these oxides have formed. So basically, what I want to get across to you is that you can do some very interesting bulk work and complement it with in situ using potentially non-conventional specimens, but it can give you independent confirmation of the diffusion-induced grain boundary migration in bulk and in situ, the Titan and the Telos STEM-EDX spectrum image data sets provided the information that we needed concerning diffusion of chromium, the significantly enhanced diffusion of chromium that had been a missing link for some oxidation-based models, and new independent confirmation that titanium and aluminum oxidation, even at those low levels, are associated with this precursor event. Now, we'll try to whip this through pretty quickly in terms of irradiation damage, which is also a really cool field. What are the physical changes? What's controlling susceptibility? And can we describe the evolution of damage? Now, the big thing about irradiation damage is one technique is not sufficient. There's a lot going on. We need to know what's going on compositionally, and for a long time that was only attainable by atom probe field ion microscopy. And now, as techniques have improved, we are still concerned with defects, any precipitation that might occur. We're interested in vacancy-related damage, and we want a bulk measure. So techniques, well, TEM, atom probe tomography, small angle neutron scattering, and positron annihilation all have a role to play along with mechanical properties. And the new techniques that we've got now are, how should I say, even rivaling the atom probe. So anyway, there was interest in this field for quite a long time, and in pure metals and just certain models, model systems on binary alloys, it was possible to do a lot of excellent work looking at TEM analyses of defects. However, in the real materials that we have to deal with, TEM was not able to identify or detect any of these classic irradiation-induced defects. So starting in the early 1980s through the present, atom probe field ion microscopy, well, in that time frame, up to and beyond with atom probe tomography, the local electrode atom probe and the EcoPOSAP continued. The research was going on, and it was well known that copper was bad. It was a bad actor. And that came from weld wires. So unbeknownst to any people until they were analyzing the welds. In the late 90s and 2008, there was more emphasis on combined techniques for characterization. So, and since 2013 and beyond, advanced analytical electron microscopes with multiple silicon drift detectors were really making a major impact in terms of providing new insights. So for those of you that might not, this is a truly atomic resolution image. This is a field ion micrograph, and this happens to be of a body-centered cubic ferritic weld all the way. This was from a surveillance sample from H.B. Robinson 2. But we can see our main poles, crystallographic poles. Atom probe specimens are needles. You probably are aware of that. But field ion microscopy was a very impressive technique. And this very tiny arrow that you see represents the entire diameter of the entrance aperture to the time of flight mass spectrometer. So most of those field evaporated ions were wasted, unlike today with atom probe tomography, where you can collect all of them. But anyway, turns out that there were solute enriched clusters that were observed or that were detected via atom probe analysis. And these solute atmospheres, which were diffuse non-random distributions of solute, were also prevalent in irradiated steels, but not present in non-irradiated steels. Looking at some other materials, bainitic, tempered martensitic steels, great toughness. I wanted to give a plug. Light optical metallography is still important, along with scanning electron microscopy. Well, what I'm going to show you is some interesting things that the industry, the nuclear industry, believed that high nickel steels and weldments exhibited enhanced embrittlement. So nickel was viewed as a bad actor. And we had an extensive research program to look kind of the whole picture on neutron irradiated high nickel steels. Well, early atom probe tomography data, it was possible to detect these solute clusters and analyze them, but also irradiate, post-irradiation anneal these specimens to eliminate vacancy-related damage. And again, we could do hardness and Paula analyses. But the bottom line out of all of this was that we discovered that manganese was controlling this nickel effect for the high nickel steels. So the bottom line was manganese made me do it. So that's our little manganese devil here. Okay. So do we have enhanced embrittlement? No, not really. We've identified the element that was crucial for the development of stable damage features. Well, how about fitting in with other techniques? And what can we do now that we couldn't do back in 2004, 2003? And how about generating similar damage features? Could we do that with proton irradiation? Let's check. Great. So here is an example, neutron irradiated damage. This is looking at A508 grade 4N steels, about 3.4 weight percent nickel, and proton irradiated steels. This is a bit higher DPA, and some HUDF images, and then looking at nickel partitioning. So we can see that we're getting nickel clustering with neutrons. We're also getting it with protons, as well as nickel segregation to boundaries and dislocations. So, and we'll notice that the scale bar here now is 20 nanometers. So these are actually quite fine. And electron diffraction did not show precipitates. This was the work of my student, Alex Carruthers, well now Dr. Carruthers. And how would this compare with atom probe tomography data? So we're working with our colleagues at Oxford, including James Douglas and Michael Moody, and they did some beautiful analysis of this steel. And we can see our nickel and manganese, silicon, and a slight hint for copper. But let's compare them. So we've got the atom probe tomography reconstruction, and we've also got the elemental map for nickel from our STEM EDX data on the Talos. And actually, they're pretty amazing. So this is like incredible what we can do now compared to what was possible 20 years ago. And we can extend that looking at various welds and things. So what we could do only with atom probe tomography. Here's EELS map from the Titan, and we can see our manganese L-edge, our nickel L-edge. Nickel looks pretty diffuse, but I would just say that if we swap this with STEM EDX, our manganese would look diffuse and our nickel would look strong just because of background subtraction. And again, don't forget the value of some discrete spot analyses, because going on to one of our clusters, we can pick up the silicon, the manganese, and the nickel very clearly, and moving just off it, they're gone. And again, the fact that we can sample larger regions, we can look at variability. So it's really amazing, an excellent agreement with atom probe data. And this is just looking at consistency of data from various irradiation conditions, various compositions, to get an idea of the fact that there are very specific elements associated with this. Now, for those of you that do atomic resolution imaging, this is some aberration corrected TEM, but yes, it wasn't possible to pick up any type of precipitate feature, even though we were complicated at some points by oxide. So this is technically what we've got, and we're still hoping to get to the nanoprecipitate side. But I hope I've been able to show you that this kind of characterization work is really important, and in our understanding of materials behavior, improving applications, and also in general, microscopy and microanalysis are so important. So my advice would be for young researchers, make sure you read the literature, make sure you question, including your own results. I think I'm the most skeptical person of my results. Be critical. Are these data definitive or conclusive, or are they just consistent with an explanation? And finally, always keep an open mind, because you never know how important observations, as simple as they may be, or as weird as they may be, could be important and a key to your search for the mechanism. This is not a one-person show. I had wonderful colleagues and students at the University of Manchester, support from various organizations, including the EPSRC, colleagues at NNL, John Hyde in particular, Paul F. Singh at Vattenfall, colleagues at Rolls-Royce, Tom Neufer, Carnegie Mellon, Protochips. And I wanted to just add a special thanks to the late Sam Grant, who introduced me to radiation damage and steels, Peter Swan, many teachers, and most of all to my late husband and our wonderful daughter, because I wouldn't have been able to do it without his encouragement and support. And with that, I guess I'd just like to thank you. And I'm sorry if I've gone over time. But...
Thank you so much, Dr. Burke. It was such a beautiful talk. Thank you for your insights. And Thank you for sharing your life with us, and the impact your husband also had in your career and your growth. That's very important to have supportive men as well as women in our lives. So we have a few minutes for questions. One is, first, thanks for your great presentation. Could you please share your thoughts on the transition from industry to academia? In light of the fast pace of scientific progress, is this still a viable option?
I personally think it is. And what surprised me, what really surprised me was the reaction of students, either my graduate students and postdocs, as well as the students, the undergraduates and graduate students in terms of teaching, because I am definitely not a career academic, and my experience is based on research and knowledge that I've gained over the years. And I was really quite surprised that the students seemed to recognize the fact that my experience came through in my teaching, my technical experience, as opposed to just telling people about other research that had been done. So I tend to populate or pepper my presentations if I'm teaching on steels or corrosion or environment sensitive degradation with actual examples of research. And yes, so I think it's great, and I think students would appreciate it. And your colleagues appreciate it too.
Thanks, Dr. Burke. Okay, another question. Could you recommend a good first step toward moving into TEM, SEM research with a surface chemistry PhD background, STM, XPS, AES?
Okay, complementary techniques are always really important. So I think coming with your perspective will give you a kind of a different view in terms of TEM and SEM, but I think it will be very complementary, and it will make you even a more powerful researcher. Are you talking about books or just getting involved in the field? In terms of books, I'd probably be looking at Williams and Carter to start out with, but if you have a colleague that is in materials, you may want to link up with a colleague and start to do some collaborative work, whereby you are doing either OJ, I'm trying to look through the comments. STM, XP, okay, yeah, those I think would be incredibly important and useful. You should be able to take some similar specimens, and start to work with other techniques, but I'd probably link in with a colleague in materials with kind of similar research interests or materials interests that you might have. And I think you'll be able to surprise yourself by getting involved with TEM and SEM, how you're going to be able to grow your research.
Okay, thank you, Dr. Burke. Another question is, in your career, how did you navigate the spectrum from developing novel techniques to applying them to solving real-world problems?
Let's see. In terms of, actually, the novel techniques tend to come about when you're working on real-world problems. In terms of my training and background, when I was at Imperial, there was a lot of work. Peter Swan had a very active group or I guess groups weren't exactly the same thing that they are now, because the number of PhD students was much smaller. But basically there was an active interest, and well, the academics were also hands-on. So Peter Swan would have sessions on the microscope, and I remember walking into the lab the first time I saw it, and John Humphreys was running a tensile test, and Harvey Flower was had a lab coat on because he was making thin foils. So that was quite inspiring to me, that people were actually in there doing things. So you could ask questions if needed, or they would give advice if requested. But basically working with conventional materials of industrial interest, you will end up getting questions about something, and you'll have to look at what type of specimens you have, and can you figure out a way to get the information that is required. So I found that it's in response to doing these types of work that you come up with maybe novel ways to approach the problem. So rather than developing a novel method, unless you've got a really great idea, which I probably I've never started out with a really great idea. It's always kind of necessity is the mother of invention.
Thank you so much, Dr. Burke. Again, thank you for joining us today. Thank you for your talk. I'm going to turn it to Steph and Tirza.
All right, thank you so much, Dr. Burke. We're going to start a short break, and we're going to put on the screen an active poll. If you'd like to participate, you can. And we will reconvene in 10 minutes.
Mm-hmm.
Great. Thank you, everyone.
Hi, everyone. Welcome back. We'll start now the research talks portion of the conference. So we will have 4 postdocs today give talks. Each speaker has about 15 minutes. Speakers, if you will, leave 2 to 3 minutes at the end of your talks, but all the participants are more than welcome to ask questions throughout in the chat. So definitely encourage you to participate that way. Our first speaker is Salva Salmani Rezaie from Cornell. So Salva, whenever you're ready, go ahead and take over.
So, hi, I hope you're seeing my screen okay and you're hearing me okay.
Yeah, looks great.
Perfect. Okay. Hello, everyone. Thank you for the invitation. It's a great pleasure to be here. And I hope everything will go smoothly because I'm presenting from the conference hall of APS. But today I'm going to talk about the correlation between electron microscopy for understanding the superconductor's normal state. We all in material science community are familiar with this materials tetrahedron, where structure connects the performance, properties, and processing of engineered materials. This structure still holds for quantum materials, but we need to consider different degrees of the freedom that are present in these structures. We can have orbital lattice, charge, and a spin degree of the freedom, and the interaction between them can give rise to different emergent phenomena and properties like superconductivity, magnetism, electricity, or topological phases of matter. And in order to understand these properties, we need to have a tool that we can investigate the correlation between a structure and property, and rather look at these property structure correlation on atomic scale. And luckily for us, we have such tool available because transmission electron microscopy techniques can be used to give us that opportunity. Electron microscopy in the past had been tried to understand superconducting states of the materials, but this rather was being very limited because we have limited options to perform our experiments, and going down to the superconducting critical temperature is very challenging. But yet there have been studies that showed, for example, this study had been done 30 years ago almost, where for the first time it showed the vortices at the niobium thin film using this Lorentz TM microscopy. And almost 30 days ago, there was another study that showed evolution of these spin texture, topological spin textures throughout the strange metal phase to pseudo gap charge density wave and going down to the superconducting state of this coupled structures. But as I mentioned, doing these experiments are challenging, and also getting down to the superconducting states where most of the time it happens below 100 Kelvin is not very easy and accessible. But then does it mean that we have to give up understanding superconducting states because the options are limited? But my answer is no, because we still can understand a lot about superconductivity if we can focus on understanding the non-superconducting state and normal state of these materials. Will upon cooling down, they will become superconducting. For example, we have a great tool to investigate the defects in these materials. And oftentimes, based on the nature of superconductivity, these materials can oftentimes, based on the nature of superconductivity, these materials can be fault tolerant or not be fault tolerant, and they can be sensitive to defects like magnetic defects. Or we have great tool to investigate the local structure in these different materials. Oftentimes these local structures are hidden from the global measurements, but we have the tool to investigate these local structures and understand whether these local structures will participate and participate in superconductivity. And also we can use this great technique that we have to investigate the symmetry. Particularly, this will become important in understanding the topological superconductors. Okay, one material system that I am going to focus on today's talk is the strontium titanate. The strontium titanate is close to ferroelectric instability, but it will never become ferroelectric unless you strain it or alloy it with different elements, and then it will become ferroelectric. Also, if we can dope it, it will become superconductor, and it shows this superconducting dome upon doping it. And as you can see here, the superconductivity occurs at the peak of superconductivity will happen at around 350 millikelvin, and the peak of superconductivity happens around 10 to 20 per centimeter cube. And this was, in fact, the first oxide superconductor that was discovered, and it was, in fact, the first superconducting dome that was discovered. But now we know that this superconductivity happens next to the ferroelectricity in this structure. But we wanted to know whether there is any correlation between superconducting state and ferroelectric state in this material, and whether these two orders are competing or cooperating with each other to have the superconductivity that we want. And this will bring up another question, that whether the nature of superconductivity is unconventional or conventional, because oftentimes unconventional superconductivity happens next to another order parameter. For example, for the case of cuprate, where superconductivity happens next to the antiferromagnetic fluctuations. In order to understand whether this superconductivity is connected to ferroelectricity in any form, we try to understand ferroelectric state of strontium titanate, and also we try to understand superconducting state of strontium titanate. For this, we looked at strontium titanate grown on a strontium titanate substrate in its unstrained form. This structure will remain ferroelectric. And as soon as we strain it and apply a contextual strain, this will become ferroelectric at 140 Kelvin. And then we looked at how much this strain will affect the displacements of titanium atom from the center of strontium, and whether there are any domain structure forming in this structure. Okay, here we go. You're seeing here two representative images of strontium titanate grown on a strontium titanate in its unstrained form. And just to mention that the dots that you're seeing are the displacement vector or polarization vector, and they are color-coded based on this displacement wheel that you're seeing here. You can see that for the case of unstrained films, domains are forming, but they are forming on very small length scale. However, as soon as we strain this film, the domains will form on the larger length scale. And as you can see, displacements are preferential along 001 direction. But we wanted to make this structure superconduct, right? And for that, we start doping these structures. As soon as we dope these structures, still these some of them where we have low carrier density, they will show this ferroelectric transition by this enhancement in second harmonic generator signal. And if we cool them down even more, go below 1 Kelvin, they will superconduct. And if we put two data points together, we can create this nice phase diagram for these structures. And as you can see, we still have this superconducting dome here. The peak of superconductivity, very similar to the bulk strontium titanate that I mentioned, happens around 10 to 20 per centimeter cube. But this time, you can see that the superconducting critical temperature is enhanced, and it is almost double of what we would get from the bulk strontium titanate. So we wanted to realize what is special in this connection between ferroelectricity and superconductivity, where we can still get the superconducting dome, but the superconducting dome has been now shifted to the higher temperatures. Okay, these are again the films that we studied. Here you're seeing the film that is will become ferroelectric at around 100 Kelvin. It has the lowest carrier concentration of all the films that we studied. And you can see that by increasing the dopant concentration, we still have these domain structure, but these domain structure are shrinking in size. And then it gets to the point that when we have high carrier density of the dopant element, then these domains are completely destroyed. And whatever we have is just random displacements of the titanium column. And just as a reminder, I showed you this for the undoped strain film, where we have very large 001 domain forming in this structure. So here you can see that by increasing the carrier concentration, these polar domains are shrinking in size, and then that is very aligned with the ferroelectric transition getting suppressed. And you can see that if we don't have any domain, we won't have any ferroelectric transition to happen at the lower temperature. So that will clearly will explain the ferroelectric part of this phase diagram, where when we increase the carrier density, the ferroelectric transition is getting suppressed because the domains are not forming anymore because of the introduction of these dopant elements that we have in the structure. But what about the superconducting state? Can we still say why the structures that superconductivity has emerged from the ferroelectric state have enhanced superconducting critical temperature, as opposed to ones that they are not emerged from the ferroelectric state? And what is this connection between these two? For that, we engineer different structures. We try to have films where they have very similar superconducting critical temperature. As you can see, all of these films have very similar, and still rather all of them have enhanced superconducting critical temperature. And as you can see here, the carrier density in all of the films are very similar. But we were able to manipulate the polarization in these structures so that we only have global ferroelectric transition happening in one of them, here marked with film A. But the rest of the films here down here, although the superconducting critical temperature is enhanced in all of them, don't have that transition to the global ferroelectric state. So if we look at, and this way with understanding this, we can understand what is the connection between this enhancement in superconductivity and the domains that might form in this structure. Okay, these are the 4 films that we have looked at here. Film A, which I showed you earlier, had that strong transition to the ferroelectric state, and you can see that domains are forming in this structure. And rather, these domains are correlated, and they are mostly directional along 001 direction. But again, for the films B, C, and D, that they are not transitioning to that global ferroelectric state, we still see that we have these correlated displacements happening in the structure. We still have domains, we still have these correlated lattice distortions in the structure, but it might be that the ferroelectric, these domains are not strongly oriented along 001 domain, but we still have very similar length scale of these domains forming in the structure. But how about the films that they don't show this enhancement in superconductivity, whether these domains are still forming in the structures? For that, we looked at the films that they are grown on strontium titanate, and also the films that they are strained, but rather they have large carrier density. You can see that for the case of unstrained film, we still have these domains forming, but compared to the strained films, they are happening on the smaller length scale. And here, for the case of doped strontium titanate on strained films, we mostly have random displacement. So that brings us to the conclusion.
Salva, 2 minutes.
That brings us to the conclusion that if we have polar domains, that they are larger than separations of the Cooper pairs, that will lead us to the enhancement in superconductivity, because the Cooper pairs that are sitting in the structure are seeing only the non-centrosymmetric lattice. But strontium titanate is not only superconducting material that we can study, we can also look at other superconductors. For example, here we have looked at potassium tantalate. Potassium tantalate is recently discovered superconductor structure, but yet there are many questions that we can answer to this regarding why superconductivity happens only at the surface of a couple of the potassium tantalate structures and not all of them, depending on their orientation. And what is the role of interface, and whether we have 2D superconductivity in these structures or superconductivity is 3D. And also I have looked at iron selenide structure, and understanding the basic structure of iron selenide will help us to explain why superconductivity is enhanced in these structures when they are next to the strontium titanate phase. But with that, I hope I have convinced you that by using different transmission electron microscopy techniques, we can understand the normal states of superconductors, and that will help us to understand better the superconductivity nature in different superconductors. And with that, I want to thank you all organizers for organizing this great conference and seminar, and happy International Women's Day to all the women out there, that they are persistent and consistent in pursuing science and pushing the limit of the science.
Salva, thank you so much, and thank you for joining us at the conference. I'm glad
thank
you were
you.
able to work that out. In the interest of time, we'll move on to the next talk, but if anybody has any questions, feel free to put those in the chat, and I'm sure Salva will be able to answer them. So up next, we have Dr. Rellie Goddard from the Woods Hole Oceanographic Institute. Rellie, whenever you're ready, if you want to share your slides and get started.
Hi, I just want to check first. I'm having a slight issue with my laptop with the fan, so I don't know if I'm worried that everyone can just hear the fan coming through. Is it okay?
I can hear you
it's not
just
too
fine,
noisy.
yeah.
Okay, yeah, it's always the days that you don't want it to that things start going wrong. So yeah, I'm from Woods Hole Oceanographic Institution. I'm currently a postdoc with Andy Cross there. And just to give a little context, I'm a geologist, and particularly I look at rock deformation. I do this mostly in a lab where I take rocks that are kind of an analogy to the natural rocks that we see either in the mantle or in the crust. I heat them up and put them under pressure, and then I squeeze them to see how strong they are. I also sometimes look at natural rocks, but in all these cases, I use microscopy to understand like the mechanisms by which these rocks deform and why they're as strong as they are. So I'm going to be talking about some experiments today, which we're looking at taking rocks to kind of depths of roughly 70 kilometers in the earth and then bringing them back up to the surface. So why are we interested in that? I'm sure most people are aware that.
Sorry to interrupt. Do you have slides to share? We don't see them right now.
Have I not shared them? Oh, I'm so
sorry.
sorry. I know.
It's a fantastic introduction, but
really, technology is not. Thank you for stopping me. That would have been really bad. Okay, here we go again. So this is my introduction slide. Move it, and this is some data, some pretty pictures to look at, which you were meant to rather than looking at my face. So yeah. Why do we care about rocks that are going to 70 kilometers? So I'm sure everyone's aware that the Earth is made up of a kind of iron-rich mafic mantle, and on top of that we have this thin crustal layer which is made up of buoyant felsic rocks, and that this crust is broken down into different plates which are moving past each other. And when you have two plates colliding, such as in the Himalayas, you tend to have one plate that is pulled down underneath the other in a process we refer to as subduction. And in this case, you have the Indian plate that is subducted down into the mantle. And as I said, these upper crustal rocks are made of felsic minerals, and one of the most common minerals is quartz, which we'll also probably all be very familiar with, which is SiO2. And as you take this deep into the mantle, you actually get a change in it to turn into a polymorph called kersite, or a phase called kersite. So this is a phase diagram where we've got pressure on the y-axis and temperature on the x-axis. And the interesting thing is kersite is a denser version of SiO2 of quartz. So you'd expect that process where you turn into kersite to cause the subduction of that plate to increase and for it to be drawn deeper into the mantle. But when we look at the surface in places such as the Himalayas, we see evidence that rocks have gone down into the deep portions and then have subsequently come back up to the surface. So you can see here a little thin section of a natural rock. We've got garnet, which is a very strong mineral, and that's surrounding a kersite grain. And just on the outside of the kersite grain, there's this ring of quartz where it's retrograding back into its low pressure polymorph or phase. And so what I'm interested as a structural geologist and someone who likes deformation is what's happening to the strength of those rocks as they go through that transition, and can that give us any indication of why these rocks are coming back up to the surface? So there's not really been much research on what happens when you go through a phase transition in geological rocks, but there's been a lot of research currently in material science. And this is an example of a really good experiment, which I love from material science, which was back in 1924. And what they did is they had these iron bars and they heated them up in the center. So you had a temperature gradient from hot in the middle to cold on the outside, and they twisted them gradually at a constant rate. And so in this top bar, where you're at 600 degrees, you can see that all the deformation is localized on that hot zone in the center. What was interesting is that as they increase the overall temperature of the experiment, so you have 900 degrees, 1000 and 1500 in the center, they saw that like the strain wasn't localizing in the center where it was weakest, it was actually localizing along a phase transformation from gamma ion to alpha ion. So obviously there is evidence that these phase transition occurs cause some sort of weakening, and in the context of broader tectonics, maybe this weakening is causing a portion of that plate to break off and a portion to come back to the surface. So we want to investigate whether we get this transitional or transformational weakening in a quartz kersite system, and also we want to use microscopy to see if we can kind of understand why that's occurring. So to begin with, just to show you some experiments which are looking at whether we can identify that quartz kersite weakening in these natural samples. We do them in a high pressure, high temperature multi-anvil press, which you can see as a schematic on here. It's known as the deformation dia. And these use really, really small samples of about 1 millimeter across in order to get to really high pressures, as I said, of about 70 kilometers deep in the earth. So we can take these rocks and we can take them up into the kersite field by raising the pressure, and then we can subsequently bring them back down. So we're going through both the quartz to kersite and the kersite to quartz transition. Now, what's particularly cool about this setup is that it's situated on a synchrotron source, which means that we're firing X-rays at the sample, and we're able to get in situ stress measurements and also in situ strain measurements by looking at X-ray shadow graphs. But more interestingly, for what we're interested in, to do with the transition from quartz to kersite, is that we can identify in situ when kersite forms, which you wouldn't be able to do in any other sort of rig or press that you have. So this is an example of a kind of lattice spacing of the material that we're deforming versus the intensities. At the beginning of the experiment, we just have this quartz peak, and then as you increase the pressure and you go through time, you can see that these kersite peaks are appearing and the quartz peak is disappearing. So we're able to like correspond the mechanical data we have with the exact moment when we're going through the quartz to kersite field. So the best way of looking at whether we get any weakening or transient weakening is to look at basically viscosity, and viscosity is a measure of a fluid's resistant to deformation at any given rate. So in this case, because we're heating rocks up and they're able to flow, it acts similar to fluid. And here we've got the viscosity on the y-axis plotted against time on the x-axis, and all these experiments are conducted at 700 degrees. And the black arrows are indicating when we're first going through the quartz to kersite transition and then back from kersite to quartz. And basically, the lower the viscosity, the easier it is to deform and the weaker the substance is. And you can see that when we're pushing the rock at a very slow rate, you see these massive drops in viscosity as you go through both transitions. But this drop disappears, or it's less significant as you push at a faster rate when you're deforming. So clearly that is a transformation weakening process that's occurring during this quartz to kersite transition, but it's rate sensitive. We can do the same set of experiments at a higher temperature to see if temperature has any effect of this. And again, when we're pushing very slowly, you see these drops in viscosity when you go through that transition, but they become less prevalent when you go to higher strain rates. So we have transient weakening in this quartz to kersite, but now we want to use microscopy to see if we can understand it a little bit more. So I should say that all of these ones we've gone through the transition twice, but because we're wanting to understand the microstructures at this point, like at the point of the transition, we quenched loads of samples midway through the quartz to kersite, so through this first transition that you can see with the black arrow.
And the first type of microscopy that we use is this microcomputing tomography or micro CT. And this is a non-destructive process. So we will basically want to get as much information about the rock before we start cutting it up. And what this does is, this is a collaborator of mine called Vera or Veronica LaRue, who's at MIT, and it's her lab that I was using. You can see the micro CT machine here, and this is actually a bit of oceanic rock that she's measuring the properties of. And you're able to, you put this in, you generate X-rays, they go through the sample. When they hit the source, they give you a 2D image. And by doing very, very small rotations in the sample, you're able to collect successive amounts of these 2D images and then construct the 3D structure of the rock. And that gives you stuff such as volume fraction, density of the particles and everything. So what we're interested in is looking at how homogeneous our microstructure is and to give us an idea of where we want to section the rock. So this is one of our samples. You can see in the blue, we've got quartz, and in the kind of green needles, that's the coesite. So we're getting a very homogeneous nucleation of coesite throughout the samples, which means we can pretty much section it wherever even. Sorry. So the next technique we're using is an electron-based technique, which is EBSD. It was mentioned earlier. This is where you fire electrons at the sample that's tilted at an angle. They go into the sample, they diffract out, and then you collect those patterns on a phosphor screen, and you get these diffraction patterns for every single point in your grain. And they give you an idea of not only which phase that you're looking at, but also the orientation of every point within the grain. So you can get grain size information from this, local, broad kind of crystal preferred orientations, and also any kind of local distortion to the crystallographic lattice. So here we've got an example of an EBSD map collected for one of those samples. These are kind of chunky sections of the coesite, and then you've got in a band contrast image on the back, we've got all of the quartz, and each of these colors represents a different orientation of the coesite. So we can get an idea of the grain size, but we're interested in deformation, so we want to look at any internal distortion in either of these phases during the transition. So we can do that again using EBSD data, but in this case, we're using something called Mr. Mean. And what that does is it takes an average orientation of each grain, and then it calculates for every single pixel, the orientation or the misorientation of that pixel comparative to the average orientation. Because we're looking at samples that we're trying to identify this transient weakening as you're deforming it, we need a null hypothesis or something to compare it to. So we did a load of experiments under what we call hydrostatic conditions. So this is where we're not deforming them as we go through the transition. And up on the right, you can also see our starting material, which is just the quartz microstructure. So here we've got coesite in the orange, and you've got this blue. Blue is the quartz. And in the hydrostatic transformation, we haven't really got any distortion to the crystallographic structure, so which is what we'd expect because we've not been deforming it. Now, if you go into the one which we are deforming, and therefore we have this transient weakening process, interestingly, what you'll notice is the quartz microstructure doesn't seem to have any deformation in it, but the coesite has quite a lot of internal misorientation. And why this is interesting is twofold. Firstly, it's against what the theory predicts, and that's because coesite is the nucleating phase, so it's the one that's growing. And you'd expect if you're growing a phase into the quartz, you'd expect the quartz to be deformed as this new phase is nucleated. And secondly, it's because coesite is stronger than quartz under these conditions. So rather than deforming the weak quartz, we actually seem to be deforming the strong coesite. This is quite qualitative, so we want to do something a little bit more quantitative. And so in doing this, we're going to look at EBSD, but taking it a little bit further by doing something called high angular resolution EBSD. And what this does is, whilst you're collecting EBSD data, you save all of the diffraction patterns, which are shown here. And then for each grain, you take a reference diffraction pattern, and you choose a number of regions of interest, which you can see here with the white squares. For each of these regions of interest, you correlate for every diffraction pattern in the grain, you work out how the displacement between, or the strain tensor, the displacement gradient tensor of each of these squares comparative to the reference one. That was not very well explained, but it gives you an idea basically of the elastic strains, which give you an idea of the internal stresses. We can also look at lattice rotations, which give us an idea of the geometrically necessary dislocations that are within these rocks, which give you an idea of how much they're deformed. Sadly, we can't do that for a coesite. We can look at the total number of dislocations in coesite, which I'm going to present in a second. And just to give people who aren't aware what a dislocation is, the simplest definition is that they're linear deflects within a crystal lattice. And you can see here I've got a dislocation wall where we've got this extra half plane of atoms. And geometrically, dislocations are ones that are necessary to accommodate a strain gradient. So if you imagine you're bending a bar, you have a strain gradient across the bit that's contracting and the bit that's extending. But you also have these things called statistically stored dislocations.
2 minutes.
So we wanted to look, okay, I'm nearly finished. So we wanted to look at the stresses that were felt by these Kerr sites and kind of quantify a little bit more, which is what we plot up here. These are internal stresses. You can see that we're getting GPA level of stresses on the grain scale. We've got quartz in the gray, and then the nice colorful things of the Kerr site. So we're seeing a lot of internal like stress heterogeneity in that sample. And the cool thing is that we can look at the shape of the probability distribution of this stress field to give an idea of whether it is controlled by dislocations, because if it is, it will follow this theoretical relationship. And to analyze the shape of the probability distribution, we do something called the restrictive second moment, which is what I've done here for the sigma 2. And I've put it up here for Kerr site and quartz. So you've got the restricted second moment on the y-axis and the stress on the x-axis. And we've done it both for the hydrostatic sample and the non-hydrostatic sample. And the only thing you really need to know about this is that if that internal stress heterogeneity is the result of dislocations which are formed due to like deformation, then you'll have a straight line at high stresses, which is what we're getting in all of these situations. And also the gradient of that line will depend on the amount of dislocations that you have in there. So we aren't able to get an exact number on dislocations yet, but we can see kind of quantify that we have a higher number of dislocations within that sample that was going through the transient plasticity comparative to the hydrostatic example. Also, because we're doing it for quartz, we can see that despite it looking like there is no deformation occurring in the quartz visually, there is a higher gradient for the one that is non-hydrostatic and comparative to the hydrostatic one. So when you're going through this transient weakening, we are deforming both the quartz and the Kerr site, but we're deforming the Kerr site more. Sadly, I don't yet have any conclusions why we're deforming the stronger sample rather than the weaker sample when we go through this. But what we found is that we've shown that we do get this like transformation induced weakening of the quartz, or when you go through the quartz Kerr site system. This could cause, and has shown evidence in natural rocks, to cause some sort of localization, potentially causes slab break off and aids aids the return of the quartz Kerr site system to the surface. And I'm going to leave it there before I say anything more inarticulately than I just did. Thanks.
All right, thank you so much, Rellie. Yichao, if you want to go ahead and start sharing your slides. There are no questions in the chat, so I'll just ask a curiosity question. How do you get your samples? Do you do any field work or?
No, so with experiments, we always use like monomineralic stuff to begin with. So not many people do, well, some more in the brittle field, people use natural samples. I have both natural samples and experimental samples, but all of these, you basically take a natural rock, which is very quartz rich, and then you grind it down and you create a powder, and then you can isolate the quartz from that powder and then recreate a rock in what we call a hot press. So yeah.
Cool, thanks. All right, if you have any other questions for Rellie, please put those in the chat. And up next, we have Dr. Yichao Zhang from University of Illinois, Urbana-Champaign. So Yichao, if you want to take it over.
Great. I hope you're seeing all the screens and everything okay. Thank you very much for the invitation and the opportunity to speak today. And I'm going to discuss my work on visualizing nanoscale phonon dynamics with 4D UEM. So many times we use electron microscopy to study structures and properties at equilibrium or at camera frame, as the previous speakers have talked about. But there are also many interesting phenomena that happen at the excited states. For example, phonon is the quasi-particle that describes coherent lattice vibration in a crystal, and it can be excited with light. So the oscillation frequency can range from gigahertz to terahertz. And phonon is a form of thermal energy carrier, and it has lots of implications in thermal transport and electronic properties of materials. So phonon can be a result of light matter interactions, so photoexcitation is frequently used to study it. So here I'm showing you the approximate timescales of photoexcitation of a semiconductor. After the light pulse begins to interact with the charge carriers, which can occur over tens of femtosecond. The electrons get promoted to a higher energy state, and then they can relax back through transferring energy to the lattice and thermalizing the lattice. The process is commonly known as electron-phonon coupling, and it can happen within just a few picoseconds. And then the coherent lattice vibration or phonon can get excited, and then later on they can propagate in the crystal. And this process can last up to a microsecond in time scale. And eventually the crystal undergoes some sort of mechanical oscillation, and then that can last tens of microseconds before the entire system fully relaxed to ground state. So photon was first studied with time-resolved spectroscopy methods in the Fourier or frequency space. The dynamics can be probed from the oscillations of signals in a reflectivity spectrum, such as what's shown here. And this provides us with understandings of phonons as a bulk property due to the limitation of the probe size, but we would like to explore things at higher spatial resolution. So to understand phonon dynamics at the nano to atomic scale, we need a technique that provides both high spatial resolution and temporal resolutions. So here's a plot of the spatial temporal scales of phonon dynamics. I then overlaid the instrument capabilities of commonly used techniques for studying phonon dynamics. And many of these techniques listed here have very high temporal resolutions and very high reciprocal space resolution. But the real space probes are often at the micron and above scale. So ultra-fast electron microscopy was then developed to really push for spatial resolution. I'll give a very quick overview of instrumentation. So ultra-fast electron microscopy, or UEM, is a pump probe technique. The microscope is coupled with an ultra-fast pulse laser system that is split into a pump and a probe. The pump gets directed onto the specimen to induce structural dynamics. And the probe is guided onto the electron source to produce photoelectron packets for imaging. The relative arrival time of the pump and the electron packet, or what we call it as the delay time, is controlled with this path length difference on the mechanical delay stage. We can then acquire an image at each time point and then stitch everything together in the correct time order to obtain a movie of the dynamic processes. Okay, so here's an example of UEM video. In this experiment, the specimen of interest is an MOS2 flake. MOS2 is a type of transition metal dicoccogenize, and this class of material is best known for their exceptional strain tunability. So as you can see, most of the specimen here is approximately along the 001 zone axis. And this thinner, brighter region on the right is tilted at about 40 degrees. And we can see some dark contrast features, and these are diffraction contrast features called bend contours. So in this experiment, we use visible light to excite the crystal. So there are two major regions of interest, or ROIs, highlighted by the colored boxes here. In this yellow box, we can see there are waves generated at this crystal-crystal interface, and they propagate inward along the bend contours. And these are the coherent acoustic phonons traveling in the in-plane direction, and we can extract an in-plane speed of sound velocity here. In the red region, however, we can see this V-shaped bend contour that's oscillating locally. And this is the C-axis coherent acoustic phonons bouncing between the top and the bottom of the crystal. And due to the projection nature of the TEM and the tilted nature of this region, we can then visualize the C-axis dynamics as the oscillation signals here. On the right is a difference image series with the same time range. We can see in the video that the onset of the C-axis phonon precedes the in-plane phonon by just a few picoseconds. And this is likely due to this initial expansion of the layers along the z-axis following the photoexcitation, which leads to the launch and propagation of in-plane modes. And this has been hypothesized and observed in simulations before, and we were able to actually directly visualize it in the experiment. Let's take a closer look at this tilted region. So if we watch carefully, we can see a dephasing phenomena of these two bend contours. And this is perhaps more obvious when we plot the position of the two bend contours as a function of time. And we call this a space-time contour plot. So the red lines here label 4 oscillation periods of both the bend contours, but the duration is quite different. And this is due to a very small difference in the thickness. So we have an equation here that describes the relationship between the velocity, the crystal thickness, and also the oscillation frequency. The slight variation in the thickness is then reflected in the mismatch of the oscillation frequency, which turns out to be 2 layers. The thickness difference is then verified by this very slight contrast in the ADF stamp image in this region as pointed by the red or the white arrows here. And further, we can really see the significant effect of the probe size in resolving the frequency difference due to the 2 layers. So this panel in the middle plots the average oscillation frequency as a function of the size of the ROI. So initially, the ROI, which is labeled in the white, only contains a uniform thickness. So there's a single frequency at 63.3 gigahertz. And when the ROI edge length increases to include regions of both thicknesses, we can then see a gradual shift of the frequency to 60 gigahertz. And also we can see this widening of the FFT peak. And the subtle effect can only really be seen because of the nanoscale probe of UEM. To build upon this observation, we started to explore more into potentially utilizing step edge to modulate properties. So first principle studies tell us that the atoms sitting at the edge experience a different force field compared to the bulk atoms. So their lowest energy states or relaxation states are different from the bulk atoms. And this can result in a modified bond length between the edge atoms and their nearest neighbors as compared to the bulk bond length. And this ultimately manifests as new electronic, mechanical, and vibrational properties. So for example, increased friction and reduced elastic constant have been reported near these edges. So this leads to the question of, can we use the unique capability of UEM to really map out the properties modulated by the step edge? So here's a UEM video of the photo-induced Z-axis dynamics of another MOS2 flake, and it is tilted at about 29 degrees. So the dashed line here mark the position of a step edge that is about 10 nanometers thick. So in this video, we can see a shearing behavior of the bend contours in the 2 different regions separated by the crystal step edge. Within each region, the oscillation is quite coherent, but things seem to be more complicated at the step edge. So of course, we can quantify the oscillations by generating a space-time contour plot and taking the FFT of the to really get our oscillation frequency. And now we can repeat this process for a series of positions along the bend contour and look at the spatial distribution of the phonon frequency. So we can see the frequency rapidly increases as we move away from the step edge, and it plateaus to some bulk frequency value. We can fit this position-dependent frequency to an upward exponential decay function here, and then obtain a frequency reduction between 1 to 2 gigahertz. And this is essentially step edge-induced phonon softening. As we discussed earlier, the frequency depends on the z-axis velocity and the specimen thickness. The velocity is proportional to the square root of the z-axis elastic constant, C33. And within each ROI, the thickness is a constant. So the frequency variation is directly indicative of the variation in the effective elastic constant. So the amount of reduction of the phonon frequency is equivalent to 2.6 gigapascal or 5% of reduction. So what could have caused this change at the step edge? So due to the unique structure of the step edge, the photoexcited layer movement is more complicated than the case of uniform thickness. So here I have a cartoon illustration of the structure near the step edge prior to photoexcitation. So after the lattice is thermalized, the layers start to move along the z-axis. And due to the different photon absorption profiles across the step edge, the amount of z-axis displacement of each layer across the step edge is different, as noted by the length of the arrows here. So we can see there is clearly a discontinuity at the step edge. However, each layer must be continuous. So the z-axis atomic movement is much less coherent at the step edge as compared to the bulk region far away from the step edge. So this incoherent oscillation directly leads to this reduction of the effective C33 elastic constant, and then subsequently the phonon softening that we observed experimentally. I then did some finite element modeling to verify the hypothesis. So the photoexcitation was simulated by applying an impulse of a z-axis strain as shown here. So the contour plot on the right represents the z direction displacement as a function of time. I then computed the FFT of the time-dependent z displacement near and far away from the step edge. So the bulk frequencies are shown in the gray, and they're pretty close to the experimentally observed values. The FFT profiles near the step edge, which are the red profiles, do show about 1 to 2 gigahertz of reduction, which agrees with the experimental results quite well. And the simulation results really confirm that our hypothesis that the incoherent atomic displacement at the step edge leads to the softening of the phonon. So in summary, we observed and quantified an isotropic coherent acoustic phonon, both in plane and in the z direction. We observed a mode coupling between the two different modes of the phonon. We also found the step edge plays a key role in the overall dynamics, including serving as the nucleation site for intralayer mode and leading to nanometer varying phonon softening. And such effect can cause up to 5% of reduction in the elastic constant. And these results really demonstrate UEM as a powerful tool for visualizing nanoscale structural dynamics and its sensitivity to subtle structural features. With that, thank you very much for your attention, and I'm happy to answer any questions you may have.
All right, thank you so much, Yichao. One quick question, Aswathy, if you want to start sharing your slides, is this a technique that's limited to, just a couple layers of material? Like I noticed you're using MOS2. Is it something that can be applied to a larger crystal?
Yes. So this basically the technique, although here is demonstrated with MOS2, is actually a bulk crystal. So it has every capability that a conventional TEM has in terms of structural characterization. So it actually has broad applications in characterizing beyond 2D materials.
Great, thank you so much. All right, our final talk is from Aswathy Shailaja, who is from the Duke University School of Medicine. Aswathy has also been part of student council for a couple of years, so excited to hear her talk about her research. Aswathy, take it away.
Hi, can you guys hear me? And my screen are like sharing, right?
Yeah, sounds great.
Okay, great. Hello, folks. Happy Wednesday to all. I'm Aswathy Shailaja, and the topic I'll be addressing today is cell viability assessment, architecture analysis of Aspergillus niger biofilm using confocal microscopy and COMSTED. What are biofilms? Biofilms are complex structures composed of aggregates of microorganisms that are adhere to the surface and stick to each other with the help of a special glue called extrapolymeric substance. These extrapolymeric substances make them less susceptible to antimicrobial agent. The biofilm cell can be coordinate their behavior via intracellular communications. Biofilms impact human life in different ways. These could include impact on cooling water system, manufacturing industry, drinking water, food processing, and medical implants. So these may lead to degradation of product quality, health risk, and contamination, etc. For this study, we are using Aspergillus niger, a mold organism, ubiquitous fungi, and industrially important species. Why this project is important? The filamentous fungal biofilms are very thick, difficult for antimicrobial agent to penetrate their structure. In order to understand antimicrobial resistance activity, it is essential to quantify live and dead cells. In previous studies, the assessment of cell viability, bacterial and fungal biofilms are determined by colorimetric assays, which is XTT, MTT. The drawback of this assay using the different stages of biofilm formation, the metabolic states of microbes changes, which may lead to fluctuation in the ability of biofilm cell to metabolize the chemical component during the assay, and these lead to the false results. The objective of this study was to visualize, quantify cell viability of Aspergillus niger biofilm without disrupting biofilm architecture using a fluorescent probe staining method and a confocal microscopy with the help of Comstat program. EPS is composed of polysaccharides, proteins, eDNA, and lipids. Here we are labeling and visualizing exopolysaccharide using lectin conjugates. The two areas of Aspergillus niger biofilm, the center and the corner portion, were selected for the comparison study and to better understand the biofilm dynamics. For the biofilm production, I followed a reproducible protocol developed by Dr. Kerrigan's lab at Clemson. According to this protocol, I used a drip flow reactor, which is a model system that can achieve the same environmental conditions similar to indoor environment or household equipments. For the staining procedure, we compile two commercially available probe staining kits that have been developed for bacterial and yeast system. The yeast viability kit, which contains classical cell stain FUN1 that exhibit orange-red fluorescence in metabolically active cell, while the dead cells are fluorescence green. The bacterial viability kit, which contains a combination of cytonine and propydium iodide. So propydium iodide is generally used for staining dead cells in a population. It can only penetrate the cell with disrupt membrane. The cytonine can enter both live and dead cells. The fluorescence signal of cytonine is strongly enhanced with the bonds to nucleic acid. When both fluorescent probes, cytonine and propydium, are present, in the case of damaged cell membrane, propydium iodide exhibits strong affinity towards nucleic acid than cytonine, and this thus replaced by propydium iodide. And the image was captured using like ISP confocal microscope. This is the confocal images of Aspergillus niger biofilm stained with FUN1. This is the center portion and this is the corner portion. In this image, the dead cells are fluoresced as green and the live cells are fluoresced as red. And in this image, orange-red fluorescence and green fluorescence combine to form a yellow-orange color, which make it difficult to distinguish between the live and dead cells. A masking effect is observed in the case of FUN1 stain. However, this is a confocal image of Aspergillus niger biofilm stained with cytonine and propydium iodide, and this is the center portion and the corner portion of the biofilm. You can see that the live and dead cells can easily differentiate as in this picture, and we can see that the center portion of biofilm contains more live cells compared to the corner portion. Notably, the corner portion contains conidigenous cells and conidiophore. And this is a vertical view of Aspergillus niger biofilm growing glass coupon, and this is the center portion. This is the center portion and corner portion. And you can see that the center portion contains more live cells. This is a result from media dripping in the surface of the biofilm coupon in a drip flow reactor, creating high nutrient concentration in the center portion when compared to the corner portion. COMSTAT is a computer program that measures the biofilm accumulation from digital image stock. It comprises of 12 image analysis processes, including biomass, thickness, surface area, volume. For the quantification of cell viability, we use biomass image analysis feature. From this analysis, it is observed that the Cyto9 PI combination stained biofilm show a significant variation in the biomass between center and the corner portion in terms of dead cells and die cells. Whereas the Fund1 stained with Aspergillus niger biofilm, the similar biomass between center and corner portion in terms of dead and die cells. The Cyto9 PA stained biofilm, there is a significant difference observed between the cell viability in center and the corner portion. So the combination of Cyto9 and Propedium ideal was found to be a reliable staining method for quantification of cell viability and visualization of Aspergillus niger biofilm. The results generated with the fluorescent probes were compared with the classic XTT assay method as a confirmatory test. From the statistical analysis of XTT assay method, it was observed that there is a significant difference in the cell viability between center and the corner portion of the biofilm. This was same trend found within the fluorescent probe staining methods. For EPS visualization, we use lectin. Each lectin is a unique protein that binds to specific carbohydrate moiety and is classified based on this terminal sugar to which they are binding. Here we are using Erythema crystallgalli, which is tagged with FITC, and their specificity towards to galactose and galactosamine residues. And another one is Cannavelia ensiformis A or CONA conjugated with TRITC, and they selectively bind to alpha mannose and alpha glucose. The exopolysaccharides are imaged according to the distinct fluorescent color with the help of confocal laser scanning microscopy. The biomass, average thickness, and the roughness of the biofilm were calculated from 3-star image using the computer program COMSTAT. As seen in this image, the exopolysaccharide distribution is not homogeneous. In figure 7 and 8, the B1 to B3, which is show the top view of biofilm on a glass coupon, and these figures indicate that the presence of higher amount of galactose and galactosamine residue, which is labeled with ECA, green fluorescent. And in contrast, C1 to C3 in figure 7 and 8, these are the bottom view of biofilm on a coupon, and the mannose and the glucose were more visible when compared to the top view. So you can see the mannose and glucose were labeled with con A, and you can see under the bottom of the glass coupon. And also we can notice that the alpha D, mannose and glucose are embedded inside galactosamine and N-acetyl galactosamine residues. From these analysis, it was also observed that the composition of ECA binding carbohydrate, which means galactose and galactosamine residue, are higher in center and corner portion, and CONA A binding mannose and glucose carbohydrate are lesser in center and corner portion, but they are varying also. We can also observe that the center portion have higher thickness compared to the corner portion. Also, you can see the hyphal structure present in here. Both the glucose and mannose can see in that hyphal structure. This indicated that the structural compound of the fungal cell wall is also present in EPS production. As seen in the figure 11, the EPS of biofilm is not homogeneous. So the roughness indicate the heterogeneity or non-homogeneous or heterogeneity of the biofilm. So most of the EPS contain galactose and galactosamine residues and less contain or smaller contain mannose and glucose. One of the possible explanation for this phenomenon is that during the biofilm formation, the hyphal network was formed. The outer layer of hyphae contain galactosamine, galactone or GAG, which is made up of galactose and galactosamine residues. This is the 3D image recreated with Imaris software. From the reconstructed 3D image, it is clear that the higher amount of galactosamine and beta-1 4 N-acetyl galactosamine is present in EPS, and the mannose and glucose are embedded inside these galactose and galactosamine residues. Interestingly, a distinct staining pattern are exhibited by ECA and CON-A. So ECA visualizes the EPS either between the Aspergillus niger cells or cell surface, but the CON-A highlighted the hyphal structure with a red ribbon appearance. Also, the CON-A also stained EPS surface to lesser extent than ECA. Moving to summary, the combination of Cyto9 and PA was found to be a reliable staining method for quantification of cell viability and visualization of Aspergillus niger biofilm. The confocal images and statistical analysis showed that the cell viability is higher in central portion of biofilm when compared to the corner portion. And the XTT assay method support the findings from the molecular probe staining method. From this, the fluorescent probe COMSTAT analysis has the advantages of analyzing biofilm without disrupting their structure. And also, the EPS of biofilm is not homogeneous. Most of the EPS contain galactose and galactose residues, and smaller contain mannose and glucose. Thank you.
Thank you so much, Aswathy. Yeah, I don't see any questions in the chat. So just, I'm not from the biological sciences. I apologize for my extreme lack of knowledge in the field. But maybe since we have a minute, could you describe something that's, like challenging experimentally that through the process of this work that you've been able to maybe learn or figure out?
So the filamentous fungal biofilms are really thick. It's very difficult to, just like taking the portion like corner and center portion. We plan initially for just using laser cutting microscopy, just cut and just make the sizes of corner and center portion. We can just cut using laser, but even the laser is not penetrating the biofilm that much thickness. So it was really challenged, this laser penetrate through the confocal. It's like through the biofilm is very difficult. So we just really need to find another way to just manually, we need to cut the corner and central portions using some blades and everything. So that was really challenging.
Oh, thank you so much. It's good to know that thickness is not just a problem for us TEM folks. Okay, great. I think now we will move into another 15-minute break before we start the panel discussions. Tirza, I don't know if maybe you have something to share before the break.
Welcome back, everyone. We popped in on all of the rooms and it sounded like you were all having some really excellent conversations. So I'll just wait another second for people to file back in. Yeah. All right. Well, thank you all for such a wonderful conference and a fantastic day. We've appreciated all of you attending, and of course, thank you to all of our amazing presenters today, our speakers, Grace, and all of the research talks and our panelists for sparking engaging conversation on all of these topics. Thank you so, so much.
We wanted to extend a few special thank yous to our awesome planning committee. So this would be Katie and Rory and Marie and Louisa and Aubrey and Andreas and Patty, and also Kelly and Mike and Yeshin for helping us today on the back end. We hope you enjoy the rest of International Women's Day, and we hope to see you all again next year. So yeah, thank you for coming.